Hello, it's Dr. Borkin, and I have the honor today of introducing Randy Sharp of H2 Sciences. Randy's primary focus is on the development, and he's been one of the pioneers in the development of methylene blue, a means of measuring the presence and quantity of hydrogen in a solution. So today we're going to have him demonstrate for us the effect on glass, aluminum, and plastic in order to dispel any aspect as far as what the end result is, and that we're getting a very high level of orally consumable molecular hydrogen. Randy, would you demonstrate for me how the tablets will be affected in each one of these different mediums?
So what we've done is we have 3 identical containers in terms of volume. They each have 500 milliliters of water. We're going to add a tablet to each, and we're going to wait a predetermined amount of time, 20 minutes, and then we will be able to, after that period of time, come back and test each one using the H2 Blue reagent and measure in parts per million the level of dissolved hydrogen gas in that particular waters.
That's wonderful. So let's go to it. We're going to test the glass first, and you'll notice this being a clear bottle, the immediate effect as far as the release of hydrogen gas in this solution.
And I'd like to mention that we've filled these bottles entirely to the top so that there is absolutely no air gap. And this is important in order to build the pressure in the bottle, which helps to dissolve the hydrogen gas.
Now, these are 3 very commonly found bottles. That's why they're being used in this experiment, because it's something that most outlet stores, most convenience stores, these are very, very common bottles. This is a plastic, this is aluminum, this is glass. So at this point, now that we've dissolved the tablets in each one of the bottles, we're going to wait approximately 20 minutes. The bottles are going to cloud, and then they'll clear, and then we'll come back and we'll measure the amount of orally consumable hydrogen. We're going now to talk a little bit about the chemistry. Randy, we've already established when we dropped a tablet of the hydrogen into the bottles, there was a liberation of gas. Now, most people are going to think that this is carbon dioxide, like in most other carbonated beverages. Please explain a little bit about how this form of magnesium is able to produce the high levels of hydrogen gas and not carbon dioxide.
Well, the best way to explain it is to look at the reaction formula. That's magnesium. H2O is water. And the magnesium reacts with the water molecules to produce magnesium hydroxide. And the gas, we're talking about hydrogen gas. And it's important to note that this magnesium is not ionic magnesium, the type of magnesium that you might find in a magnesium supplement. That would be Mg++, ionic form. This is elemental magnesium. It's an atom or a metal of magnesium.
This is what makes this product so unique in the elaborate way that supplemental magnesiums are used in order to create this high level of elemental magnesium that
Correct.
is incredibly safe and yields a very, very high level of concentrated, orally consumable molecular hydrogen.
Correct. And the hydrogen gas is easily visible. When you drop the tablet into the water, you can see it being formed. And although it might look like carbon dioxide, it is in fact.
It's very
hydrogen gas.
impressive,
Yes.
as we had seen before
Yes.
when we first dropped the tablet.
Yes.
And that's why there's a certain period of time that it takes for that tablet to completely develop, and we see that cloudiness occur within the solution before it clears, indicating that it's time to consume
Correct.
the beverage.
And during that time, an important thing is happening. The hydrogen gas is actually dissolving into the water in nanobubble form in order that when you drink it, it will enter into the stomach and into the bloodstream. And we want that dissolved hydrogen gas.
Of course, and we want it delivered in a small enough fashion for it to be able to be absorbed freely into the system.
Correct. We call those nanobubbles, hydrogen nanobubbles.
We know that magnesium is absolutely essential to life. And in the last couple of years, it's now well recognized and established that most individuals are magnesium deficient. Anybody who gets a muscle cramp, for instance, has experienced magnesium deficiency within that muscle, which allows for the muscle to relax. We have a twin benefit here of not only is this producing hydrogen, but it's also producing a form of magnesium that's much easier to absorb in its ionic form.
Yes.
Would you just pencil out the chemistry behind magnesium in this conversion?
Yes. If you remember from our previous equation, we had magnesium plus water yields magnesium hydroxide plus H2. This is the added benefit you're talking about, because we now have ionic magnesium, because magnesium hydroxide dissociates in water into ionic magnesium and hydroxide. So now we have a most bioavailable form of magnesium.
Well, and what you just said is that what this is doing is creating the active form, so the body
Yes.
doesn't have to take something such as a supplement of magnesium gluconate and convert it into its active,
Exactly.
ready-to-use form.
Exactly. This dissociates readily in water and is bioavailable immediately into the body. And there's no other process that has to occur, as you say, in a more complex molecule to separate out the ionic magnesium.
Well, it reduces the amount of energy that's required in order to actually use the magnesium that's yielded in the use of these tablets.
Yes, it does.
All right, so we've waited the 20 minutes that we discussed earlier. Now let's get a read on these bottles.
We're going to be using the reagent we discussed earlier, the H2 blue.
H2 blue, and we're starting with the glass container.
The formula for H2 blue requires the sample size be 6 milliliters. The beaker is graduated in milliliters.
All right, so you're pouring off the 6 ml.
All right, get it as close as possible.
No, it's okay.
And then we start adding drops one at a time.
And again, explain that each drop is having a specific effect as far as measuring the concentration.
Yeah, so that's 15 drops. And as we discussed on the whiteboard, the hydrogen in the water has consumed those 15 drops.
Mm-hmm.
And it's still clear, so we know we haven't reached the end yet.
18, 19, 20, 21, 22, 23, 24.
You can tell it's slowing down a little bit. And I'm going to call that 25 drops, or 2.5 parts per million.
All right, now we're going, since we've looked at the glass, let's look at the aluminum next. Oh, I can hear it.
You can hear the pressure release.
Sure.
Once again, we're looking for 6 milliliters.
All right, so again, there's 6 ml of water in the testing tube. And we'll go through the same process. And you'll notice each time that the H2 blue hits the solution that there's a clear component under it. And how many are you at now?
That's 22. And the last one is 23 drops.
So we're at
2.3
2.3 parts per
parts
million.
per million.
All right, so now we're going to look at the plastic bottle and the parts per million that it will yield. Now, keeping in mind, this is a premium grade plastic bottle versus the typical thin plastic that most people are going to find in their convenience store. This does allow for some of the hydrogen to leach out. We've selected this plastic, so we're going to get possibly a higher level than we would in another plastic container.
Once again, we have the release of the pressure. And if you look closely, you can see a little bit of effervescence as the hydrogen attempts to equilibrate with the atmosphere. Pour another 6 milliliters.
All right, so we've got the same quantity, the same testing beaker. We're going through the same procedure here.
It's 22. I like to see it turn clear, and that has, that's 23, which is the
So
last
we're at 2.3 parts per million in a premium plastic container. Randy, we've looked at the various containers, the plastic, the glass, the aluminum, and we've established an amount as it relates to the hydrogen that develops within that kind of medium. Would you explain right now a little bit about how methylene blue is used in the detection of hydrogen in a water solution?
Yes. So the reagent, the h2 blue, contains a compound called methylene blue, which is an oxidizer. H2, as a reducing agent, is able to combine with the methylene blue. So if we wanted to depict it, methylene blue being blue, of course, when those two combine, in other words, the H2 gas, as a reducing agent, combines with the methylene blue, it forms leucomethylene blue, which is the clear form of methylene blue.
So we would expect that when you add the reagent, that if the hydrogen is present,
In
That
sufficient
is-
quantity,
it's going to clear the solution.
correct. So as we add drops into the hydrogenated water, the drops that are blue will turn clear and continue to do so until all of the hydrogen in that sample is consumed.
All right, so it's pretty straightforward science
Yes,
most sixth graders should be able to understand.
yes. And the way we calculate it is that 1 drop equals a 0.1 ppm, or milligram per liter. So all we have to do is count the number of drops it takes for the solution to remain blue. If it takes 10 drops, 10 times 0.1 equal 1 ppm.
That's great.
Yeah.
So this is what we're looking for, is the quantity of drops that it requires in order to clear this material.
Correct.
Great.
Got it.
So let's see how that works.
Okay,
So Randy, you saw it. You tested the 3 bottles, the 3 different mediums. You saw that the tolerance was minimal between them. And in actuality, the testing procedure is very elementary.
Yeah.
With more sophisticated equipment, we would be able to measure a higher level of that which is escaping from the containers.
Right.
So explain to me just briefly and recap what we saw between the variants of the glass, the aluminum, and the plastic.
The glass, as you remember, 25 drops.
2.5 parts per million.
2.5 parts per million. The aluminum, 23 drops. 2.3 parts per million. And the heavy-duty plastic that we used was also 23 drops.
2.3 parts per million.
That's a very small variance for a titration where you have the possibility of having a very slight plus or minus difference in the sample, for example. 5.99 milliliters instead of 6 or 6.01 milliliters. A drop size, maybe a different pressure could make
Of course.
these are
And
very small
We also
differences.
know that under the proper conditions, we would expect to see much higher values as well. So this is, for theoretic purposes, worst case scenario of what you would actually see in the field using the methylene blue approach
Yes.
as a reagent to test the hydrogen content within those 3 mediums.
Yes, and I would add that these are considered very high levels of hydrogen gas, which we achieved in a very short period of
And
time.
That's a very, very important point. And in the future, we'll look at some of the other containers that are being used as a means of establishing how high these levels really are.
Yes,
Really appreciate your help today.
my pleasure, thank you.
Your expertise always impresses me, and we need more scientists like you out doing this kind of work. Thank you again.
Thank you very much, my pleasure.